Welcome back, everybody, to our Nirvana stage. If you just joined this stage, my name is Rokas, and I'm moderating this amazing stage. And I'm very excited about all the speakers that we have. And this next one has an amazing presentation to present to you. If you have any questions during the presentation, please leave a comment and let us know. We'd love to answer to all of your questions. If we don't have enough time, we will go to a separate room, which is chat with a speaker room. So you will have an amazing chance to talk privately to our next presenter. So our next presenter is Michał Łusiak, and he's a software developer from Poland, currently living in Sweden. On the daily job, he works mostly with backend for web or mobile applications. He has worked with many programming stacks, but currently focuses mostly on .NET. Big fan of functional languages, recently interested in machine learning and data science, aviation geek, skier, and wheels of furry. So, Michał, the virtual stage is yours.
Thank you, Rokas, and welcome everybody to the third day of the conference. This hopefully beautiful morning wherever you are. It's not very nice in Sweden today, but we're all inside, so that's a good part of it. So as Rokas mentioned, my name is Michał. I'm going to speak today about solving 3 business problems using ML.NET Microsoft Machine Learning Framework in around 45 minutes. I always like to start this presentation, my presentation, with this photo. It's from International Space Station because it shows 2 places I consider home right now. As Lukas mentions, I come from northern Poland, somewhere here, and now I live in southern Sweden. And Lithuania didn't made it to this photo. It's somewhere on the left down corner, but we're not that far away. So I'm going to start this presentation about talking what is machine learning, what is AI, maybe what is the difference and how we perceive it and how I perceive these differences. Because quite often when you look into the media and you hear about AI, it kind of looks like that. It's this scary thing that will gonna come to us in the form of Skynet or some other being and will take over our lives and enslave us. The reality looks more like that right now, that we're looking a lot about formulas, graphs, and charts, and trying to make sense of it. There's also a joke running on Twitter. It was tweeted by Matt Veloso, that if it's written in Python, it's probably machine learning. If it's written in PowerPoint, it's probably AI, and it kind of comes from this perception that engineers and data scientists turn to call it more like machine learning or using specific algorithms they're using, and business people who like do presentations and stuff like that, they tend to use more like hype words, and AI is this kind of not well-defined hype word. Also, we can look at this, that AI is quite wide term and can encompass a lot of things, but machine learning is part of it. This is just like one of the ways to do AI, and deep learning is even more specific. Deep learning is doing machine learning using deep neural network, something we're not going to focus on today, but it's another term that drops around quite often, so it's you know, good to see. So if you look at our AI definition on Wikipedia, it's quite fuzzy and not very specific. It's basically like saying that it's intelligence demonstrated by the machine, and it shows like some human-like features of that intelligence. But in the 40s, we already considered this artificial intelligence. This is ENIAC, which is a computer used by US Navy for calculating ballistic tables for the artillery. That was its main goal initially. and now our phones have more computing power than these machines. Then in the 90s, when Garry Kasparov was beat by the computer program playing chess, this was something we consider artificial intelligence. But now we kind of understand how it works. You can search like the tree of options for the chess game for like 7-8 steps ahead quite easily, and from computational perspective, chess is a solved game, and we don't really even look at this anymore as artificial intelligence. And a couple of years ago, AlphaGo beat another challenge, which is like the game of Go, and even recently it's doing very good progress in playing StarCraft against human people. But the more we understand how this works, we kind of like it stops being like magical. We kind of don't consider it artificial intelligence anymore. It's more like we've known the subject, and this AI seems like this white rabbit that's we're chasing, but we cannot catch ever. And machine learning is about like a scientific study of algorithms and statistical models, and it's in opposition to like classical writing of algorithms. We don't write the algorithm. We use the patterns to generate algorithm automatically, sort of. And there are a few ways to approach. There are a few types of algorithms in machine learning. The most common is supervised learning. Is probably the most researched and the one that's used the most these days. And the way it works, instead of writing algorithms that will change input data to output data for our program, we're doing something different. We take sample input and sample output data. We use a step called training to generate that algorithm that we will later use to work on the new data we haven't used for training. So this is basically using and finding patterns in data to build algorithm automatically and use it to predict outputs for the data we haven't seen during training. And one of the most common tasks used in supervised learning is regression, and it's most commonly shown because it's relatively simple. So let's say we want to, and regression is about predicting like a single number. So for example, for we want to predict a price of apartment given its size in square meters. And as you can see, this data is somehow like linear. So if you like, so if we apply function to that data, we can probably find a new point somewhere on that line and predict price for the data we haven't seen. Another type of task is classification. So we have like a group of data points, and we can divide them in the groups. So for example, like find a nice apartment somewhere outside of town, and so on, depending on the type of features we provide into the algorithm. Another whole group of learning, and there are like much more algorithms. I'm just like dropping samples here. Another type of algorithms that's very exciting is unsupervised learning, because it doesn't require labeled data. So we can have like input without prescribed outputs, which is problematic for supervised learning, because you have to spend a lot of time preparing data and getting data sets that are labeled. So have those sample inputs matched to sample outputs to produce the algorithm. In unsupervised learning, there's no problem like that, but also this area is not super well researched yet. But we're more exciting because it doesn't require so much human interaction in the process of making it. And one of the sample tasks is clusterization, so finding a type of similar data points in the data set. So you can, for example, find similar apartments or similar customers of your product to make offerings for them and so on. So how actually linear regression work, which is like the simplest algorithm using supervised learning. Let's say we have data put on a two-dimensional chart, and on the horizontal line we have parameters, so kind of input data. And right now we're using only kind of function with one input, just because it's so easy to visualize. With more input data, we get adding more dimensions. So like with one input, we have 2 dimensions. With 2 inputs, we have 3 dimensions. With 3 inputs, it starts to getting complicated to visualize, because it's not easy to visualize 4 dimensions, but math will take anything. So you're going to work with data sets that have like 400 input data. So it's really hard to visualize that. But as I said, math will take it. So we have, this basically, is described like a function, although not really, because for each parameter you have some value, and to have a function, you have a straight continuous line. So for each value on the bottom, you have some, for each input value on the bottom, you have some age, so you have some output value. And linear function has 2 parameters that describes it. It's a and b, and a is responsible for the angle of this function. So if a equals 1, it's a 45 degrees function. If it's more than 1, it's a higher degrees. If it's less, it's lower degree. And b is responsible for the kind of offset on the vertical line. So if you look at it, of those 3 examples, and like, assuming that, the older you get, the more money you have on your account. The first example is like steady growth. The second example is like much higher growth, because your function is growing faster. So basically, it's just like a sample, you have like better job than the first example. And the third example is like you're starting with some money already in your account. So let's say you're born into the rich family. Give an example. Although in data science we don't use A and B, or you'll find somewhere, but it's more common to use actually W and B, because it fits into the naming convention, as W are the weights for the input and B is the bias, so all the information we didn't include in the kind of function. And one of the classic examples of using linear regression is predicting how much you're going to pay for the taxi, because there is some sort of linear relationship. Basically, you pay for kilometers traveled or for time traveled, depending on how the system is set up wherever you take the taxi. So we're looking at our data. We have distance as an input data, and how much we pay as the output. And we usually start by drawing a line with some W and B, either randomized or we take a good default. And we know we're a bit off, but we need some like mathematical way to determine that, because we want to automate it. And we look at it physically, but algorithm doesn't see it. So we try to calculate something called cost function or error function that will tell us how far away we're from the fitting the data the best we can. And one of the commonly used function is the square error, which it's not super complicated function, but when you see this like sigma and square and so on, it's getting complicated. But the reality is this is like a for loop. If you look like in the programming version. So what we take the difference between each of the actual values and the predicted values, we square them up, and we sum them together. So when we know how bad we're doing, we can actually try to fix it and get this line closer to the data set. And you can visualize it also on a like kind of three-dimensional graph when we have different values for a and b or w and b, which describe our functions. And for some of those values, the square errors are like really high. That's not where we want to be. We want to find ourselves where the square error is the lowest. We'll never get to the perfect like kind of error zero situation if the data is not perfectly linear, but the goal is to get as close as possible, to have a function that approximate our data set pretty well. And effectively, we'll have to like find ourselves down that bowl to minimize those values. And when we do that, we'll have a linear function that sort of well matches our data and allows us to predict like, on average, good approximation of what we're going to pay for the taxi. So if we take, 20 miles, we're going to pay this amount of currency. All right, so let's look at ML.NET, which is Microsoft approach to doing machine learning. It's relatively new, although it's nearly, I think, 2 years now when they announced it. It's pretty high-level API, and it's looking at stuff from the perspective of the problem we're solving and not like algorithm we use, although you also have control over that. It's a code-first approach. We're writing code here. There's no drag and dropping like some other Microsoft solutions on Azure especially. And Microsoft claims they use this technology for quite some time in Bing and Excel and other their products. And they just productize it for other people to use. It's free to use, open source, cross-platform. It's written in .NET Core, so it works on Linux, Mac, Windows, with different tooling situations, but it generally works. So they announced it like in May 2018, and 2019 they released version 1.0, and I think we're at version 1.5.2 right now. It's production ready. It's constantly developed. They take pull requests. It's a very, very interesting project generally. Unfortunately, it doesn't support like usage of neural networks directly. You can import trained models from TensorFlow or ONNX models, although for very specific cases like image recognition and so on. This part it's still being developed, and they're looking to a good way to incorporate this. But my understanding is they're not planning to focus on neural networks at this point. So when you look at the model of working with ML.NET, there are like few steps we're gonna work on, which are generally matching the steps you perform in a data science project in general. So we have like something called transformers, which allow you to like morph your data to the shape that's more useful in that case. So basically you collect and load data, and there are multiple like data loaders. You can load your data from SQL, from text file, from CSV file. We create a pipeline that basically generates like work tray data to format it, remove things we don't need in the data set, replace missing values, and so on. Add some additional fields. Then we use stuff to train model. We evaluate the results. If we're happy, we can save that model. If not, we can just continue it to get the better results. And then we can use that saved model for the second part, the inferring. So basically like using that trained algorithm for the stuff we need. And model can be saved, for example, to the disk. You can save it to database. And for example, if you have that trained model, using it, it's like instant. So Usually in machine learning, the training part is the one that takes time and the computational power. But if you have your model trained, you can just use it, for example, in your web application to get constant, like very instant answers to the. So, for example, you build your sales prediction model, and then you want to show your manager some sales graph, and we're gonna get them in the web application without any issues. All right. So if you look at code of those steps, usually for most of problems, it looks like that. We'll have those 5 steps. First, we create ML context, and this is just the object we'll pass around that will contain information about the our build model and so on. It's a bit like a DB context in entity framework. It's kind of similar idea. Second part is to get our data from wherever we have it. Here I use the load from text file function, but as I said, there are like multiple ways to do it, and documentation is very good how to do that. Then we build our kind of prediction model and our data pipe. So in these things we just basically take features out of the text and do like binary classification, and we use specific classifier, which is like the segregation. And the fourth part is basically training the model. This is the most computationally intensive part, but it's fairly easy in the code wise. And then in the step 5 we use prediction using this model. So we can find answers to the questions we wanted to ask in the whole data science process. So let's look like again at this example we started with, looking at linear regression, how it's going to look in code. And all those samples come from this GitHub machine learning samples. This is basically like around 20 application and just code samples that show how you can apply ML.NET to different cases in your daily problems. So it's very, again, a very like problem approach. So very good to start with, and those samples are very well described and so on. So the data we have for the trips is like we have some fields with what kind of is the vendor, so like taxi company, what is the rate, how many passengers were going. Those things probably won't have that much impact on the price, but trip time in seconds and trip distance in miles is probably much more interesting. Then we have like payment type and so on. So that's our input data. So first thing, we're gonna load that data from text file. We have a type taxi trip that will that allows us to have like kind of strongly type approach to that input. And after that, we try to remove data that's like not very easy to or maybe problematic in that set. So for example, in here we're removing data points that their taxi rides are more than $150 and less than $1. So those could be like erroneous data, or we decided this is erroneous data. So this shows how you can like filter some data out, and usually these steps will be quite complex, when you do those samples or using some simple data sets, they're usually quite good. They have all the filters and so on. When you deal with the real data, you have to, polish that data much more usually, because the real data usually have a lot of problems. Then we're building like using the transforms to build our data model properly. So we use a fair amount as our labels, so basically as output data, and then we work with some other fields, like for example vendor ID. We decided to one-hot encoding it because even though it's like a numerical value, it's some ID. We don't really want the algorithm to treat it as numerical data because we know it's like more like category data. And if it's algorithm treated like as a numeric data, it could decide that, oh, this company has ID 2, which is better than previous company that has ID 1. We don't want this assumption, so we can basically mark some data that's like categorical data, and that's what we're doing in those fair lines. Then we also do normalization. So let's say you have passenger values that are between 1 and 20, and basically the numeric algorithms work better if the data is all in the same scale. So instead of being from 1 to 20 for the passenger counts, and like distance being from like 1 to like 300, it's better to have them, for example, all normalized from 0 to 1. It's just like better from numeric perspective. Okay, and then we pick up the type of trainer we're gonna use. As you can see, we'll take ML context, and then we go with the type of problem we're trying to solve, which is regression. And then you can see what trainers are available. And you can do the usual .NET stuff when we press the dot and we hope for the best, find algorithms that you want to try out, the kind of dot-driven development. And the next step, we just train the model. As I said, it's the most complex computationally, but in the ML.NET, it's just one line. They do all the stuff we need there. And then we do evaluation that allows us to see the results and print some metrics. So basically see how the results look. So those are the metrics for regression. We can see the value of our loss function, look into R2 score, and a few other things. Those are the things that can tell you how well the algorithm is performing for the data, and you can decide you want to do some other algorithm or use other algorithm, depending on if you're happy with the results or not. And yeah, as I said, you can, when you press the dot, as always with .NET, you can see what's happening. So you can see that we have a bunch of problems to solve, like clustering, anomaly detection, forecasting, and so on. And the samples project I showed before has a lot of good examples how to apply those things. Okay, the second problem that's quite common in retail is product recommendation. So something you can see quite often, for example, when you do shopping on Amazon or wherever, that people who bought this product, they also bought those two other things that you don't need in your life, but maybe you should buy them so we make more money. And the input data we use for that is kind of like this matrix of things that were bought together. So basically, if 0 and 1 are in the same line, which means the product ID 0 and product ID 1 were bought together on this specific like receipt, for example. And the algorithm that's used for that is called matrix factorization. And we this time load text file again, and it's in columns, so you can see how you can like format the data from columns in the text file. It has a lot of approaches to the input data and a lot of formatters and so on, taking CSV files, JSON files, XML files, SQL databases, and so on. So wherever your data is, there's probably a way to load it from there. And now we are setting up some options for the matrix factorization. Most of the algorithms have some options to set up. They usually have decent defaults, but sometimes you want to mess with them. And interesting thing is called alpha. Alpha is the learning speed in machine learning, and like the intuition is you want the learning speed to be as fast as possible, but it's a kind of wrong intuition, because it basically represents how big of a steps you do to reach that bottom of that bowl to minimize the loss functions, as I mentioned. And if you make those steps too big, you will always miss the bottom of that bowl. You will never get there, so you won't properly optimize the function. On the other hand, if you do steps too small, it can take like ages to optimize. So it's a bit of like fine-tuning. And alpha is like one of things called hyperparameters. So this is like parameter that's tuned to calculate the parameters. And initially, like with the alpha and other hyperparameters, those things, seems like values that doesn't make sense. But the more you do like specific algorithms, you kind of gain intuition. What are usually good values for those hyperparameters? And yeah, step 4, we're picking the type of algorithm we're using, matrix factorization, as I said. We train it and we see some values. And for here, prediction, we can see like what's the value for the product 3 and 63. And we get some magical number, 0.4. So this also shows that using the algorithm is not a golden bullet. Like it doesn't do all the work for us. We still have to do something with it. So now you would have to calculate those values for all the pairs of the product and probably sort them, and for product 3 just show to the customer maybe 20 most important. So it's not about what the 0.4 mean. You just you have to find those that are the highest. So even though we run some algorithm, now it's second part of the work that we have to like prepare. So one of the clients, when we applied this and it actually worked really well, we have like a step in the continuous integration pipeline that every week on weekend we calculate that from the last few months of data, and then we can see some seasonal changes, for example. And we just prepared tables of like 20 most common bought together products for each product. So it was all prepared in the database after calculation, and we just reached to that database when presenting the product page. So again, we trained the model, and there was also some steps after that training to prepare that data for presentation. Customer segmentation is another interesting problem when you want to put customers that, for example, do similar purchases together, for example, to send them similar offers and stuff like that. And let's say you have like customers that you have some offers that were offered in your store, and you have some customers that bought that offers, and then you can make like a matrix out of it. And we're gonna use k-means, which is basically like finding kind of the clusters of similar data points in the space of data. And the steps are the same as always. We do some data preparation, then we create the training pipeline. That's very simple here. We fit it or train it, and then we use that data to run an evaluation and shows our metrics. Another problem that's quite common in Riemann is demand prediction. Just for example, you want to have stuff in store before people like buy everything like that. So for example, before Halloween you want to have some Halloween costume stacks and so on, and those things are obvious, but when we work with customers, also find some things that maybe are not so obvious and interesting using those algorithms. And the way it works, there are a few approaches of it, but basically this example comes from the bike sharing application, and what they have a lot of data that's like weather data, but also which weekday the bikes were borrowed and so on, and based on that they can do some predictions. And here we're using we load the data as always, again from text file in this case. We prepare our data in the second steps. And then there are multiple algorithms to do it. We can do it using regression like we're doing here. We can also use like, if you're looking into more like long-term seasonal data, there are other algorithms to use. And here, another cool thing about like ML.NET, that you're not bound to one algorithm. We can actually load into table multiple algorithms that we're gonna try, and we're gonna run a for loops over all those algorithms we put into the table. And for each of them, we're gonna do the same steps. We're gonna train the model, evaluate the accuracy, and we're gonna save that data. And then we can compare how they're doing between each other and say, okay, for this data sets, actually the fast tree regression was the best algorithm to use on that. But since you can do it, maybe why not automate this? And then another cool thing in ML.NET comes into the function, just like AutoML, which basically does it for you. Instead of like saying you want to do a specific algorithm, you say you want to experiment on regression, and what it will run, it will basically, you decide for how long, and we're just gonna run for maybe 60 seconds and so on, and we'll test as much regression algorithms possible, and we'll also try to test at different parameters that you put into those things, and present your result, which algorithm is the best for you, the current data. So basically, knowing just what kind of problem you have to solve, is like regression to predict one number, or is it classification to put your data point into one of the buckets, or so on, allows you to automate that process. So that's really cool. And then when you decide which is the best, you can, for example, pick that's the best model. You use that trained model to run predictions, which is great, but maybe not always responsible to just run it automatically. And yeah, that's the get out. We predicted $15.5. The actual offer is $5. So nice. Okay, but since we already written this with code, maybe it's not so hard to even automate it without code, and that's what Microsoft did with Visual Studio. So basically, you have your project, you add machine learning, you pick type of problem you have to solve, you load your data, you train it, you wait some time. It's basically gonna run this algorithm to finding the best training model. We evaluate the data, we add the code to projects, it auto-generated, you have machine learning added to your project, boom. So that's very, very interesting. It only works for few type of problems, I think mostly regression and classification. It's really cool to, like, you know, very quickly add ML to your project. And then there comes the question, is it like responsible, and should you do it with your project? And I'd say it depends. If you're like working with like medical data that will decide about people's lives, that's probably not the way to do it. You should be more responsible. You have people working on those like algorithms who know what they're doing. But if you're like, you know, want to show something on your website, or you know, experiment a bit with like suggestions on the sales page, there's probably no harm in it. And it's always like, you know, depends. So I'd say it's good to try, but it's also be cautious. Remember that you know, those features are quite experimental still, and you know, be responsible about it. So that's all from me right now. Thank you for listening, and have a great rest of the conference. And I'll see you in the room after the presentation. Thank you.
Thank you, Michał. Thank you for your presentation. And as Michał said, he's waiting you in a chat with a speaker room. So up to 9 people can join Michał with their cameras and microphones on, and you can continue these discussions. Yeah, that's it for today, guys, I think, from Michał. And we will see you in the next presentation shortly. Thank you, Michał, again.
Thank you.